Swayam Prabha. Digital India. Educated India.
So we continue our lectures on estimation of system frequency. Today we will conclude the part on estimation of system frequency, and next time we start on a fresh topic. Now before we conclude, just to refresh our memories, we will go through all that we have done in the past couple of lectures, and then we come to the we have seen that there are some approximations and assumptions that we have made, but today we will come to an exact method using three-phase signals. But before we do that, let us quickly revise what we have done in the past couple of lectures, and then we conclude this series of lectures on estimation of system frequency. Now, so we are looking at estimation of system frequency. In that, so far we have done DFT of complex exponential. Then we saw that a complex exponential is not of much use because our power system signals are either real sines or cosines. So then we saw DFT of cosine signal. Then we saw moving window approach, or what we called generalized DFT, just for our terms, moving window DFT of both complex exponential and then moving window DFT of cosine signal. And then very briefly we saw estimation of system frequency using that approximation. We will quickly just for the sake of revision go through all of this and then conclude this lecture. So we started with complex exponential, DFT of complex exponential. So our signal was of the form E is equal to j omega naught of t, or E is equal to j 2 pi f naught of t. I am not going through all the steps because this is just a revision to refresh our memory so that the whole estimation of system frequency can come together as a snapshot. Okay, we also defined if we have n number of samples and which are obtained in p cycles, then we saw that n f naught is equal to p. Then the x of n becomes E is equal to j 2 pi n p by n. It becomes independent of the t, the time at which the samples are taken. And then xm, the DFT, which is defined as will then become, again not going through the whole derivation again, but n e raised to j pi p minus m into 1 minus 1 by n sinc of pi p minus m. These expressions may seem a little tedious, but once you get the hang, okay. So this part then the DFT should have been n in this case, but this part is the angle leakage, and this part angle error rather, and this is the magnitude error. Okay, what happens if when the frequency changes from f0 to f, and this is of course only the magnitude of x of m, and you can see here that for very small changes of frequency, the magnitude leakage is very small. Okay, however, the angle leakage can be quite significant, is what we saw last time or one lecture before that. You can go back and refer to that. We will again not go through everything in this lecture, but you can see here that for small changes in frequency, the magnitude leakage is quite small. Okay, and the slope near say m is equal to 1 is also small, so that is why the magnitude leakage by that logic also is quite small. Okay, then we went to the cosine signal. As we said that, you know, in the, at least for our power systems, in our world of power systems, the signals are either cosines or sines or cosines. So we have simply assumed a unit magnitude and cosine of omega t or omega naught of t, which is cos of 2 pi f naught of t, and we then related it to, or we rather wrote it in the exponential form as E is equal to j omega naught of t plus e raised to j omega, and we said that this also introduces the concept of negative frequency. Okay, or in other words 2 pi f naught of t plus minus of, this is minus sign, f naught of t by 2. Okay, again not going into the whole definition derivation here, but x of m will then give us half of this where did I? Okay, so this gave us n by 2 e raised to j pi p minus m 1 minus 1. This part we already knew, this part sinc of pi p minus m upon sinc, sorry, p minus m. Okay, and for this part we simply replaced m by minus m, p plus m minus this is sync. Okay, then here too we saw that for values, if p is close to 1 and m is 1 or integer multiples, this will go to 0, and then the magnitude leakage is almost similar. We will see a graph of that also. Here you can see for a real cosine signal. Here of course what we have done is we have taken the frequency variation to be quite large. That is from 50 hertz it goes to 40 hertz and 60 hertz. Then you can see that here the change in magnitude is quite significant as the frequency deviation is large. Of course, in a 50 hertz system you do not expect frequency to go to either 40 hertz or 60 hertz. So it will be it should be closer to 50 hertz, like 48.5 and say 50.5 or so. So this is just shown for the sake of illustration that the leakage that can occur can be quite significant in this case. Okay, so we see the amplitude response here. This is only the magnitude, not in terms of the angle. So now we go back to our main task of frequency estimation. For that we then went to the moving window approach. And for the moving window approach we will directly work with the of the cosine signal, DFT, moving window DFT of cosine signal. Okay, so we named it x of w for the wth window. X of w of m. Here the index changes from, instead of 0 we have same n samples, but the index now varies from w to n plus w minus 1 for the n samples. And then we have the rest of the components are okay. We replace p by minus p here, and then what do we get? We saw this again. I request that you should do it for yourself and see, so that so we get this extra term here. This 2 pi w by n will be a common term which will be there with the entire series, so that we can take that as common, and then I'm sorry, there will be a term here. Now this is our for this series we have already derived the DFT here. This is what we have derived. So we'll just replace that. We just get two extra terms here. So for a real cosine signal, the x of, for the wth window, we get n by 2 e raised to j 2 pi. Okay, so this is w. Please not to be confused with omega. So let me write it a little differently. Minus m e raised to j pi p minus m into 1 minus 1 by n into sinc of pi p minus m upon sinc of pi by n p minus m. The second term similarly will be n by 2 e raised to j 2 pi w by n p plus m e raised to minus j pi p plus m into 1 minus 1 by n sinc of pi p minus p plus m upon sinc of okay. So again, using the same logic for m equal to 1, p close to 1, that is f by f naught, very close to 1 if the deviation is very small. This second term will what will it be? It will be, for say p equal to 1 and m equal to 1, this will go to 0. But for p close to 1 and m equal to 1, this will second term will be very, very close to 0. So this term will disappear. So we get x of again w e raised to j pi. Okay, this should be 1 since we are taking x of 1. Into sinc of pi p minus m upon sinc of pi by n p minus m. In this class, of course, we didn't look at what the sinc function is. The sinc of x is defined as sin x upon x. Okay, if you remember from the last few classes. Anyway. Okay, so what would be, then we saw what if for the next window, this is approximately equal to n by 2. Everything else will be the same except that you get w plus 1 here into p minus 1 e raised to j pi. I'm just writing it so that we get very comfortable with the expression. Otherwise I could have simply divided the two expressions upon sinc of okay. So what does that give us now? All the terms are the same, only we will get okay. So what we are saying is for every window that is incremented, the angle will be incremented by 2 pi by n p minus 1 for the fundamental frequency. If it is the mth frequency we are talking about, then it will become p minus of m. Okay, so which is nothing but, we saw this again, we will have a look. This is 2 pi by n f minus f by f naught minus 1. So f minus f naught is delta f. So we have e raised 2 pi by n delta f by f naught. Okay, so 1 upon f naught is t naught, and t naught by n is the sampling interval ts. So we have e raised to j 2 pi delta f ts. Okay, and then we saw that of course we also discussed a few things like, since the angle is incrementing, if we are talking of things like distance relays where we do v by I, or the power where vi star, where the angle information is not used, then this doesn't matter because both the phasors will be rotating at the same with the same incrementing rather with the same angle. Okay, but when here we are using this specifically to our advantage, this leakage, to determine the system frequency. So what do we get if we look at the this is the DFT, but if you look at specifically the angles, then delta f ts, or in other words, now what is this? This is actually nothing but d psi by dt. Now since this kind of differentiation is difficult, what is usually done is this angle difference is accumulated, okay, to say some value, say 0.5 radians or so. Okay, and the t to and the time to accumulate that is noted. So what we have is 2 pi delta f into t is say 0.5 radians, and then delta f 0.5 upon 2 pi into t. Okay, and say if we say average it over 4 cycles or so, or average it over 4 windows, then what we will get is 0.32 upon delta f. Okay, so yeah, so this is actually where we stopped. The advantage of this method, of course, also we discussed, was that you don't need to go for other the other methods, of course, are one popular method for estimation of system frequency is zero crossing. But as we said, if there is noise or if there is pollution with harmonics, etc., the zero crossing can be a little erroneous, and that too the zero crossing is averaged again like this over 3 or 4 cycles. So so the that method can be erroneous. So that is why, of course, there you will have to correct for the shift in frequency and then look at the zero crossing. That method is also followed, but here the advantage of this is you don't have to, you simply use the DFT leakage that is happening to your advantage, and then use that to estimate the system frequency. So here this is where we had stopped last time, and we will continue here. This, of course, as we saw, has an approximation. What is that? That is that we have ignored this second term here, okay, which is for small deviations in frequency, and like the ones which we expect to encounter in power systems, because our frequency deviations are not generally very large. This method is could be accurate, or is rather more or less accurate, but to get a very accurate method and to work without any approximations, we now make use of three-phase signals. Okay, so for three-phase signals, we could either use the current signal or the voltage signal, but generally the voltage signal is preferred for calculation of system frequency, because the current could contain harmonics, acharacteristic harmonics, and in general more noise. Also, the current can vary over a large extent throughout the day or any period, because the load can vary. The voltage, on the other hand, does not have so much of pollution with other frequencies, and also it is irrespective of the load, it is there. The voltage is usually held in a very narrow band. So that is why for calculation of frequency, voltage signals are preferred. So what are our three voltage signals? V of t, say cos omega naught of t plus phi. We could take phi as 0, but let us generalize it as far as possible. That is why we have taken some phi here. This is Vb of t. They were taking three phases, and Vc of t is Vm cos of omega naught of t by plus 2 pi by 3. Now, without any loss of generality, we could actually use these signals only. These signals only. Vm can be considered as unity, okay, or normalized unity. Doesn't matter, because we are just calculating system frequency here. So in our overall treatment, this will not matter at all. Again, we have the same treatment as below. So we have n samples in one period t0, which is 1 by f naught. That is assuming that the system frequency is f naught. If the system frequency is f, this is what we have. This is the same as last time, but repeating it just to system frequency changes to f is f, then we obtain n samples in p cycles. P is equal to f by f naught. Let me write it clearly. Okay. Okay. Now, for the timing, let's if say our signal, instead of, we will just talk of complex exponential for a minute. Let's get back to a complex exponential before we go back to our main point of interest here, which is the cosine signal. 2 pi, or say in this case we talked of omega, but omega is nothing but 2 pi f naught of t plus phi. Okay, we didn't talk of this, which is nothing but okay. So for this we already know the DFT. Okay, so we just get I mean this will be common to all the terms there, so we will just get this as n e raised to, you can do it for yourself and see, I'm not going through the whole derivation again, but or sorry, x of m okay. Now if x of t on the other hand is cos of omega naught of t, or let me write it from the beginning itself as cos of 2 pi f naught of t plus phi, then this of course can again be written as half of f naught of t plus phi plus minus f naught of t plus phi, okay, which is nothing but okay. So now you know where we are getting at. This we have already seen here, the DFT for this part, that is this part. Similarly, we have seen the DFT for this part. We will there will be simply a common term which is e raised to minus j phi there. So what we will get here is, when you take the DFT of this, is you will get n by 2 e raised to j phi e raised to j pi minus p minus m1 minus 1 by n sinc pi p minus m upon sinc. Again, you know, these expressions do seem to be a bit tedious, but once you get used to them, they will appear quite routine. Into sinc of pi p plus m upon sinc pi by n p plus m. Okay, and if we have now the moving window, this is for the first window, or x of 0 if we could call it the first window. If we have the moving window, then if we have the moving window approach, then w, you will get one more term. You know, in all this you will have one more term which is depending on the, everything else remains the same, 2 pi n w p minus m into e raised to j sinc of pi p minus m upon sinc of pi by n p minus m e raised to minus j phi e raised to minus j 2 pi n w p plus m e raised to minus j pi p plus m 1 minus 1 by n sinc of pi p plus m upon just writing it in a more readable fashion, sinc of pi by n p plus m. Okay. Now now this part which we have been seeing from earlier, okay, the phi part and the moving window part, removing that, the this part, okay, we will for simplicity of treatment and for easier readability, we will write this as A, okay, A e raised to j phi y, you will soon see, and this part we'll write as B. Okay, where A is what we have derived earlier, n by 2 j and B of course is the same with the P replaced by minus P. Okay. Okay. So is that clear? Now this is xw. Now what we will do is this we will designate as xa of for the A phase. It could be the voltage, current, anything. We said voltage earlier. So just for the sake of generality, we will write we will maintain x. It could very well be VA W of m. Okay, so this will become okay. Now what will be x b of m? We will replace phi by phi minus 2 pi by 3. Okay. Plus b. This is again that is why we used that is why we used A and B, so that we can focus on these things rather than get confused in these other exponentials and sinc functions. Okay. Okay, so this can be this I'll write it so that it is a bit more readable. We are still talking of xm of b. plus b e raised to minus e raised to j 2 pi by 3 e raised to minus j 2 pi n 2 pi by n p plus n. Okay, this is minus and minus, so this 2 pi by 3 comes here with a positive sign. Here it comes with a negative sign here, and here it comes with a positive. Similarly, x c of m, this is for the c phase. This is w, for the wth window. Then you will get a e raised to j 5 plus 2 pi by 3 in this case, and j 2 pi w p minus m plus b e raised to minus j 5 plus 2 pi by 3 e raised to minus j 2 pi by n p plus m. This will again, you will have, if you take this out, you get e raised to j 5 e raised to j 2 pi by 3 e raised to j 2 pi w by n p minus m plus b e raised to minus j 5 j 2 pi by 3 e raised to minus j 2 pi by n w p plus m. Okay, so now we have the operator a, which we have defined. If you remember our lecture on symmetrical components, we have the operator a, which is e raised to j 2 pi by 3, and in turn a square is e raised to minus j 2 pi by 3. Okay, so here these can be replaced as, what we simply get here is xa w, of course, is a e raised to j 5 p plus m. X b w of m is a e raised to j 5 into, this will be, first one is my a square now, so here it comes as a square plus b, then this will be, the second one is plus j 2 pi by 3, so e raised to j 5, then a, okay, and then e raised to j minus j 2 pi by n w p plus m. Similarly for a, because it is j 2 pi by 3, then this should be minus. If I have made a mistake, a square p plus m. Okay, so now we have defined our the DFT of three phase quantities. Now assume that because of some frequency unbalance that the system becomes, the frequency change, the system becomes unbalanced. If it is balanced, then your positive sequence phasor will be given by the XA itself, the A phasor also itself, if we are talking of A as the reference phasor. If not, then X. Now we'll take the positive sequence X. Okay, so I will not write it as 1 because we already have for the first fundamental frequency, so we'll write it as X positive W of M is given by XA of M plus A X. Sorry, I made an error in the notation. XBW of M plus A square divided by 3. Since A is the reference phasor, what we are doing is aligning everything with A. Say this is XA, XB, XC. So this we are rotating by A, and this we are rotating by A square. So this is what we have done, if you remember the symmetrical component treatment. And now what will we get? Let's do this and see what happens. So everything else is the same. This is the same, only you have we have these A e raised to J phi e raised to okay. So this is this gets multiplied by 1. So we have 1 here. The second term gets multiplied by A square. Sorry, A. Okay, so you already have a square here. A square into A is A cube. Okay, and for the last XC you have A here. You are multiplying that by A square, so you get another A cube. Okay, divided by 3. Now what we saw what is A, and A cube is equal to 1. Okay, so this becomes, we get only this part will be left, because since this is 3 divided by 3, you will get 1. Now what happens to the second term? Okay, similarly here also there are the common part we will take out. P plus M, and since the first term is multiplied by, is multiplied by 1, so we get 1. Then the second term is multiplied by A. Okay, so you already have A here. Okay, so you get A into A square. Okay, the third term gets multiplied by A square. You already have an A square here also. So A square into A square is A4 divided by 3. Okay, so now what is A4? A4 is A cube into A is equal to A, and then what is 1 plus A square? That is equal to 0. Okay, so the second term here is exactly equal to 0. So what are we left with? So earlier we had some second term which we said will go to 0 under certain circumstances, like very small deviations of frequency. Here, because we have taken the positive sequence, the DFT of the positive sequence phasor, here the second term exactly goes to 0, and we have now if we take the fundamental frequency phasor, then what we will be left with is and we will then use the same, this is one we said fundamental frequency. Okay, and then we'll use the same not a trick, but we'll use the same approach that we used last time, positive sequence. If we divide that, then this is common, this is the same. What we will be left with is simply p minus 1, where p is f by f naught, so that gives us f naught ts, where ts is t naught by n, or 1 upon n f naught. Okay, so then what do we have here now? Okay, so now we'll use a similar approach that we used last time, or rather the same approach, not similar, that angle of the but keep in mind that this is not the phasor quantity but the positive sequence quantity. We have used that to get rid of the approximation that we were using so far, and delta f. Okay, and when we said that we will accumulate the angle, we will not do a what is a differentiation kind of approach here. So we will accumulate the angle to say 0.5 radians, and this will then become, let us keep this as ts. Upon 2 pi into t. Okay, and t is so, and then depending upon whether the rotation is clockwise or anti-clockwise, you will get f naught plus minus. Depending on the sign of this, you will get f is equal to f naught plus minus f. So whether the frequency is higher than your nominal frequency or not will depend on the sign of delta f. So this is how we calculate frequency or calculate system frequency from DFT leakage. So this ends our treatment of calculation of system frequency, and also our lectures on DFT. We will continue with some new topics and advanced topics from next time. We will look at wide area measurement systems. We will also look at some fundamentals of protection. So whether we look at that next time and look at advanced topics a few lectures later, we will decide. Okay, so thank you. This is the end of the treatment on system frequency.